This is done in several steps. I will first invite you to have a look over here. Here again, how a DC fault, the consequence of a DC fault in a network. This is supposed to be the DC source. These are the transmission means here, especially this one here. This is the load. Energy is transferred, power is transferred from here to here. Everything is fine. We have the breaker here. In this very simplistic sketch, we have inserted suddenly a fault, for instance here to ground, which means there is no more load. What happens now? This sees no load, so the only thing that happens is that power is still provided here, which means the current increases and the energy is transferred into these elements here of the network. These elements are the transmission elements in the network. There is no more load here. As we were saying earlier, the current keeps rising and you have to catch the current during its rise and to bring it down somehow. This is done by our circuit breaker, who inserts an element that opposes a voltage that is higher than this one, which acts sort of like a brake. If you want to have a mechanical equivalent, it is like if you are having a race car which has something which is running faster and faster, and the only way to stop is to insert a slope to it. So this is sort of mechanically inserting a slope such that it slows down and stays afterwards still. That's the goal of it. Now, going back to the electrical operation, we have here the main branch, which is operating when we have this situation here. Power comes in, goes out here. The goal here is to have the minimum losses, the minimum amount of losses. This is why we associate power transistors, which we'll come to later. These are the very fast elements. This is a disconnector known to be very low impedance, so very low losses. This comes with higher losses, but being faster. And we have other branches in parallel, 3 of them. One here, what we call temporization branch. This is the branch in which the current will be diverted in order to have this opening without any load. That's important in order to reduce any electrical erosion on the contacts. But this opposes a very low voltage. So from outside we will see that this here is as if nothing happened, but only for a very short amount of time. Only for the amount of time necessary for this disconnector to open. And we will see that this is the key. This is the key for DC interruption. I'll show it later. Once this is able to withstand the high voltage, the current is running here. You want now to oppose more the network voltage to the whole system. This is done in this branch here. This is switched on, the current is commutated in this branch, and here we have a capacitor which is fed by the magnetic energy in the network. The energy which is here in magnetic form, you can see this energy by the current that it drives and the voltage that is uploaded here into this capacitor. So here the voltage rises very rapidly because the current is already at a high level. Once the voltage here is high, the whole current commutates into this surge resistor here, which has the function to absorb the energy from here. When the current is running here through this one, we have reached this point here. This function to absorb energy is something that is not a function in an AC grid. There in an AC grid, it's the source that does that. Here it is the breaker that has to perform that, because as we said earlier, the sources only pour energy in one direction. They never pull it back. If we go a bit more into details and to put some real physical elements behind this, these are the following slides.
Because in fact what is important is this element, which is a mechanical disconnector, and all these branches, in fact, they are used to wait for being able to go in this one with the surge arrestor in serving the network. And when the current is growing, we want to cut the connection, but this is mechanical, and it is not fast enough to sustain the voltage which could appear if we start to open. So we need to create some branches, what we could say delay branches, so that the current is going here. This is opening, it takes time, and this is creating some voltage which is sustainable by this equipment. After this one, and this is continuing to grow, and when this is completely open, it is sustaining the full voltage, and it's possible to insert the surge arrestor, which is making a counter voltage to the energy generation. And when it is in the network, the current is going down, and it is extinguished. So this is the principle of this complete equipment. And I'm saying it's not very fast, but it's a question of hundreds of microseconds. So not very fast, but quite fast anyway. Huh?
Completely electric. There is nothing with spring with it. We minimize the mass and the whole system. This is why the whole system is actually the drive and the linkage in between has completely been redesigned. Just because you have to be fast, you have to lose mass. What we call main branch here is the one, this back chassis over here. The power transistors are these big here. We're putting 2 of them in order to make it bidirectional. It has power electronic components in them, which by nature are unidirectional. So if we want to have bidirectionality, we put 2 anti-series. This here, the ultra-fast disconnector, is this part underneath here. You see that it's quite modular. You have several connected in series, which means if you want to increase the voltage, you put more in series. It has some current rating, but you see that these stripes here are different current paths. If you want to reach higher ratings, put more or less current paths in parallel. This was the main branch. Going back to this temporization branch, there's the chassis in the back. These thyristor-type power electronics are these stacks that are hanging here. The surge arrestor and capacitor are those guys over here. The next branch here, the arming branch, is the one that rises the voltage, starts opposing or starts exceeding the voltage of the network, which means you stop the current from rising. This is a very important function. That's the chassis here in the front, and this capacitor here has to withstand the full voltage of your network, which means you need a bit more in series. Last but not least, energy absorption in the extinguishing branch. These guys over here, these are commercially available surge arrestors, nothing new. This is a first design made from scratch during a European funded project based on Alstom technology. However, within 3 years from the design that was numerically simulated, we had to make it, and without any standard, without any test procedure, without any test circuit, we also had to make the whole thing happen, make it real and test it, and the results are just behind you. So all this within 3 years, which explains why we have not optimized for size yet. But you can trust me that we would, of course, never put these chassis to earth between high voltage parts, which makes the whole thing extend. So this as a product will become much smaller. This is a zoom onto the test oscillogram. We have had since this was done with RT in the project, they wanted to have not only interruption tests, but they also wanted to have DC current tests, so temperature rise tests, overload tests, dielectric tests. So we have tested open, and closed, and while opening. It's not only a one-shot mock-up from the test. We tested during 2013 here for DC currents at 1500 and overload 20 minutes at 2000 amps, overload 2 minutes for 3600 amps. which shows you that there is still some slack. And for rated current, we haven't pushed it to the limits yet, but we can most probably go around the 2000 amps. For the voltages, the rated voltage here is a demonstrator voltage just to show that it's modular and we can adapt to any of the constraints which we have in the network later. Well, this was inherent a bit to this. The new function with the energy absorption here, this value shown here is not at all limiting. It has to do with how much energy is in the network when interruption is requested. And we actually had the possibility to absorb 4 times more than that.